Greetings. I'm going to talk about the geometric shortest path algorithm. It has geometry in the title here, and I'm a fan of geometry, but this is specifically a graph theory problem. So this is a kind of graph that's different from the high school graph that you've seen. We are specifically focusing on the idea of algorithm. This is a process for doing something. So this is going to tell us a process for finding the shortest path in this geometric representation. So step one is to identify your starting vertex or point. And so we're going to start at A and we're going to move over here to Z. And we want to do that by going the shortest path possible. This is a weighted graph, so each of these curves on here, these lines, these are called edges. They each have a number associated with them. And that you could think about if this were a map, this is the number of kilometers that you have to travel to get from one place to another. And so we want the shortest distance we have to travel. So we want something that's economic. So the first part of step one of the algorithm is we're going to circle the point that we are at. We're going to circle that vertex. And then from the circled vertex, we're going to look at the weights of the edges that are here, that are incident to this vertex. And we're going to choose the smallest weight, and we're going to highlight that edge. And then we're going to circle the vertex that is incident to the edge that we just highlighted. So this vertex here. And then the next step of the algorithm is you look at the circle of vertices and you look at the weights that are incident with those vertices and you choose the smallest path, or the smallest length of path, the smallest weight. And so it might be that we need to come back and reevaluate here. So we have a total of 10 from this vertice to the next vertice. If we go from here to here, we have a total of 13 here. If we go from here to here, we have a total of 14. And if we go from here to here, we have a total of 16. So we have a lot of weights here to consider once we just get our second vertice identified. All right, before I go any further, I need to define path in relation to graph theory, and we also need to talk about the algorithm. The algorithm itself is not an efficient algorithm. We're going to end up with some extra edges that we don't actually need in the final solution. So we need to keep that in mind, and we're about ready to see that with our second move here. Path in graph theory, we're specifically looking for a simple path, and that is that no vertex and no edge is going to be repeated in this. So being that this is not an efficient algorithm, there's some things that we're going to throw away after we've gone through the entire algorithm to actually see what our final solution is. So we need to keep that in mind. As we look at the vertices that are adjacent to the vertices that we circled, we see that we have B, D, J, and K that are all adjacent vertices. If we look, the next move here, we would go from 7 to 6 for a total of 13. We could go from 7 to 7 for a total of 14. 7 to 9 will give us a total of 16. And then just moving this one move is 10. So we can easily see that we would rather go 10 kilometers for one move rather than 13, 14, or 16. So even though we've just decided to move this path, we're going to go back to the start and restart. And that's illustrating part of the fact that this algorithm is not efficient. We've made a choice, we've done the choice according to the algorithm, but now we're going back to the start and essentially starting over. So this algorithm kind of allows the idea of a false start. So now we have two vertices that are circled at the end of our current path. So we have essentially two different places that we're looking with this algorithm now, and the algorithm is helping us choose the best paths, and then the ultimate best path at the end is going to be the solution to our problem. So if I go from here to here, we have 19. If we go from here to here, we have 16. That'll both those paths put us at vertex J. So right now we're looking at this being the best. The other option is that we can go 14 or 13 again. So looking at 19, we need something smaller than 19. This is 16, 14, or 13. 13 is going to be the shortest. All right, so maybe we want to kind of keep a tally at this point. You can make the set of vertices that you have and then make that equal to the weight so that you can kind of keep a tally for your own self to help you keep track of things. So I have A, C, B right now. And that's giving us a total weight of 13. All right, so right now, AK is our shortest path. All right, so we're looking at going from B to D to add 8 to our total. That would be down here. Or we can add 9 here to have 19. All right, so our next best move is going to be to go to J. And so we have AKJ now. So we are looking at either adding 9 or 7 onto that. 7, of course, being the smaller value. And Z is right here. This is where we're trying to get to. Over here, I would be adding an 8 to this. So adding 8 will put me at 29. Adding 7 will put me at 26. So that's going to be what we want there. So A, K, J, Z. It's going to put us at 26. Another path that I missed originally but was discovered by one of my college students, Monica C. There is a path ACJZ, which gets us from our initial vertex to our terminal vertex. And this has a better weight. This has a path weight of 23, which is our geometric shortest path. So this is our shortest simple path within this graph. Something I want to point out is if we had gotten down to a point where we were at this vertex and there's choices of 2, in this algorithm, if you have a choice where the two weights are equal to each other, you can arbitrarily choose which one that you want to do with that. That's kind of an interesting twist in this algorithm, is that you have arbitrary choices when you have equal weighted edges. So hopefully this has been helpful in explaining how the geometric shortest path algorithm works. These edges here that we highlighted earlier are throwaways. They're not a part of the solution. Even though we follow the algorithm and it generates these highlights, they're not part of the solution. That's why this is not the most efficient algorithm. Cheerful Calculations.